All right, guys, in this video, and hopefully it's our last one, we're going to be talking about 160.3 and how that relates to 160.1 and 160.2. So 160.3 up here at the very top, you're going to see that they're calling this total residue. It doesn't say anything about filterable. It doesn't say anything about non-filterable. It just says total. That's all that it is. So in a way, in a nutshell, 160.3 is almost like 160.1 and 160.2 put together, and that's why we call this total residue. So imagine that you are someone that's paying for a service, and that service is to just get an overall dirtiness of how this water sample might be. Like, how much residue is there, and I want the overall picture. I don't need you to do a filtration step where you're telling me, oh, this is how much solid went through a filter paper, and this is how much solid stayed on top. I don't need any of that information. Thank you, but no thank you. I just want an idea of the overall dirtiness of what this sample might bring to the table. And hence, this is the total residue aspect of what we're doing here. So if you did want just information on the TDS, which is the dissolved solids, then you can only pay for 160.1, and that is a test that we will do, and that's the test and the data that we will report. If you wanted also to know information about how much suspended solid was there, okay, well, that's the other method, 160.2. It's the stuff that stays on the filter paper. But if you did not need us to categorize what is filterable and what is non-filterable for your results, for however you're going to use them, then you could request just do a total. I don't need you to separate them out into two different categories. Just do a total residue and call it a day. Okay, great, fine. How is this any different than what we've already done? Like, what steps are going to be different? What steps do we take? Blah, blah, blah. All right, so as before, it looks like total residue, and then it says gravimetric dried at 103 to 105. So this is the lower temperature settings of what we saw. If we looked at the temps for 160.1 and 160.2, the 103 to 105 was on the lower end of those two choices. And this total residue is going to go with the lower end of those two choices. So this is the temperature of the drying oven that I would want to pick if I was doing a total residue test, which is 160.3. Total residue can be abbreviated as TR. Next up, instrumentation is just a drying oven, as expected. Section 1, the method is applicable to drinking surface and saline waters, domestic and industrial waste, same as before. 1.2 says the practical range of the determination is 10 to 20,000 milligrams per liter. I hope you did that sound effect with me. So again, these are ppm values. So notice in the first one, it was 10 to 20,000. So this matches that. In the other one, it was 4 to 20,000. So that was a little bit bigger. It included a little bit more numbers. And what this method does is like, oh, okay, well, the limit here was 10 to 20,000. I know the other one could go a little bit lower, but we're somewhat restricted because the first one only could go to 10 and nothing lower. So that is going to be replicated here for 160.3. Summary of method, it says a well-mixed aliquot of the sample. And keep in mind, aliquot just means portion. That's all that means, okay? So a well-mixed portion of the sample is quantitatively transferred to a pre-weighed evaporating dish and evaporated to dryness at 103 to 105. Notice it doesn't say anything about stuff getting filtered. There's no glass fiber filters. There's no filter apparatuses. There's no filter flask that are going to be used here. It's just simply, let's shake some water up. Shake, shake, shake. Woo, woo. Shake, shake, shake. Woo, woo. Shake your cylinder. Woo, woo. Shake your cylinder. Woo, woo. Okay, so that's what goes on here. That's what we want to do. So we're going to shake the sample, and we are going to just transfer it into an evaporating dish. That's it. Nothing more. Definitions: total residue is defined as the sum of homogeneous suspended and dissolved materials in a sample. Section 4, sampling and handling as before. Do them as soon as you get them, but if you can't do it for whatever reason, you need to keep them cold on transport as well as while they're in the lab until you get to those. Section 5 is interferences. It says non-representative particles, such as leaves and sticks and fish and lumps of fecal matter. So we've seen that before. If this is not traditionally found, then you need to maybe pluck those out of there. Good luck with the fecal matter. And then 5.2, floating oil and grease. It says if that is present, then it should be included in the sample and dispersed by a blender device before you aliquot it. So that is something slightly different here than what we saw in point 1 and point 2s. Section 6, evaporating dishes, 100 ml capacity. Again, they give me a couple of choices. So pretty much the same kind of evaporating dish that I used in the other method. Section 7 says procedure. Heat the clean evaporating dish to 103 to 105 for an hour. And then if you want that volatile residue, you need to heat it at 550 for 1 hour, but we're not. That's not what the purpose of this method today is going to be. Cool, desiccate, weigh and store in a desiccator until it's ready for use. Again, as before, these are probably going to be pre-cleaned for you. So we will have these ready to go, and you'll have that evaporating dish. You're going to assume that this has already taken place. We've taken a dish. We've hoped that it's cleaned. We're going to heat it for an hour. We're going to cool it. So that way we can make sure enough, all of this stuff is kind of driven off. That saves you an hour of time. 7.2 says transfer a measured aliquot into the weighed dish and evaporate to dryness on a steam bath. Very similar to some of that other method, 160.1, right? We're going to have a steam bath. We're going to put a crucible on top. We're going to let it evaporate off. Not a big deal, not a problem, but that's what we're going to do. 721 says choose an aliquot where you can at least get 25 milligrams of residue that's going to be left behind. So if you need to use more than 100 mils, use more than 100 mils. Or if you want to scale it down, you can scale it down, but you kind of want a target here of at least 25 milligrams of residue that you're going to be gathering here in the very end. 722 says, if the evaporation is performed in a drying oven, the temperature should be lowered to 98, so that way you don't boil and splatter the sample. So now all of a sudden, oh gosh, they're giving me a choice. If I don't want to do it in a steam bath, I can put it into the oven. And if I put it into the oven, I just need to lower it down to evaporate the water slowly, so that way we don't scorch and char the residue that might be left behind. Yeah, that is an option here if that's what you want to do. We didn't quite see that with the other two, but we see it with this one. But we got a steam bath going, so we might as well just keep the steam bath going, folks. 7.3 says dry the evaporated sample for at least 1 hour. Oh no, another hour. Well, hopefully you're going to process all of these samples together at one run. So that way, when you walk over to our ovens, you're going to have the method 160.1 dish in the oven at the same time that you'll have the 160.3 dish in the oven. So that way you're really only waiting 1 hour for both of these to dry. So that way you can take them out and cool them in a desiccator. And then it says repeat until you get a constant mass. And of course, we're not doing that unless we tell you otherwise. But keep in mind, it does require at least a second round of heat, if not more. As before, we want to make sure that we get 0.0005 grams difference or less. That is what we're after. Calculation, very similar to what we saw before, right? So it looks like we're going to take our A value, which is the dish plus the stuff, the residue, in milligram, and we're going to subtract just the dish that is cleaned. Do that difference. Multiply by 1,000 as before. Get a number. Divide by C, which is the volume of the sample that you used. And for us, most of the time, it is 100 milliliters. And then, ding! Excel, in a proper lab environment, Excel will do all the work for you. Here, you're going to have to kind of tell Excel what you want to do with the numbers. We're forcing you to walk through the calculation yourself. And that will give us our value in milligram per liter, aka parts per million, which is ppm. All right, so it looks like 160.3 is just pretty much shake a sample up, pour 100 milliliters of that sample in a dish, and evaporate the water off as much as possible, and then take it to the oven and dry it. There's no filtration step. So again, the total residue is going to be the total suspended solids and the total dissolved solids put together, because we are not separating them in this particular method and the way that it's written. So just an option for people to go by. This is an overall dirtiness, if that's how you want to think of it, as far as the water samples go, even though that's not really true. But you can think of it that way, at least for now. But it's just an overall idea of how filthy and nasty this water might be. And we are looking at residues, which are a lot of times salts and that type of material that might be behind, that's going to stay behind after the water evaporates off, of course. But other stuff could also be there. It's just, that's too much detail than to what to go into now. We save that a little bit later in our program. Details matter. And here, getting used to a method, getting used to kind of the first time that you're seeing proper methods being implemented, following directions as they're written, that's going to be more important than some of these proper definitions that you might see. A little bit later down the road, we'll clear that up. All right. All right, so those are the differences between 160.1, 160.2, and 160.3. Before I let you go, I want you to see some pictures at least of what we're talking about. So in these methods that you've seen for all of them, they've talked about filter. Well, there's multiple different things that can be used. If you've never been in our lab before for CTC 114, this is what we are calling a Buckner funnel. It's going to be porcelain in nature. There's little tiny holes at the very bottom of it. And that helps kind of prevent the paper from ripping, I would say. But the problem is that if you choose too big of a holes, then your paper can rip, and that can be an issue, or that can be a problem a little later down the road. In the right-hand side, you're seeing the filter flask. And that's a 250 milliliter size filter flask with a side arm. And that's going to be connected to a pump. That's going to be connected to some type of vacuum or aspirator. And that's going to be pulling air through the funnel. And it's going to help pull your sample through the filter paper much faster because of that. So that's what we are referring to as far as a basic filtration system goes. Now, what we'll use could be this, or it could be a little bit different as far as the types of material we have on hand at that moment. So if it doesn't look exactly like this, don't freak out, but the mechanisms of how that filter is going to happen will be the same. It's just sometimes we've got a little better situation that we have at our disposal, depending on what we have on hand and how much money or that our budget has, in order to see if we can get things that are maybe disposable, one-time use, that we can filter samples through and throw them away, so that way we don't cross-contaminate. So we'll see the day that you come into the lab, and yet again, I will show you either way that we use those. I will show you and demonstrate one of the samples before you get started on that day. Next up, we talked about glass fiber filters. This is what a glass fiber filter looks like. They are a little bit thicker than a regular filter paper that you will see in our lab, and they are somewhat kind of spongy sometimes if you actually feel of them with your bare fingers. The filters over on the right-hand side in that picture, that is what we mean when we say that these pore sizes are varied. You can see areas or voids that are much larger than some of the other areas. That is just how glass fiber is made. Normal filter paper is not done that way. Normal filter paper is more controlled. The holes of the filter paper, or the lattice of the filter paper, is going to be somewhat controlled, somewhat uniform, but not in a glass glass fiber. So anything that's dissolved will normally make its way through this glass fiber filter, and then the larger particles do stay behind, but again, keep in mind that the holes are very varied. So that way, the majority of that sample can possibly go through. As long as it's dissolved, it will be able to escape. Next up are desiccators. Two different kind of styles of desiccators that you'll see in the lab. Over here to the left are the more what I would call the single use. And this would be a smaller desiccator that's more personal, that you will have your samples in. And then down at the very bottom, that's kind of what you're not seeing here. Down at the very bottom in this area of the pitcher, you would have some type of desiccant. And that desiccant is going to absorb any type of moisture that might make its way inside of that container with that sealed lid. And that sealed lid is very important. Often there is some type of grease that is over the lids, and that is very important because that grease is going to prevent all of that moisture from making its way to the inside. So that greased lid is going to give you an air kind of tight seal, and then the desiccant that's going to be down there at the very bottom will absorb any moisture that might find its way in as you open and close the lids for sure. And that could be silica, or it could be special types of desiccants that we use. There's different materials that can go on the inside. It just really depends on what the lab needs and what they prefer to use, and what material they're using with. Sometimes they're told what to use. Excuse me. Over on the right-hand side is more of a tower type of desiccator. Notice it's got multiple shelves on it. And those multiple shelves like this, that is great if you need to store multiple types of material on the inside. And those multiple types of material, it just gives me more room. It allows me to place more samples on the inside, so that way they're not just single type of use desiccators. But folks, these are very expensive. And of course, the larger that they get, the more expensive they're going to become. So you want to be careful when you use those desiccators. And you also want to make sure that you are using something that makes sense. So for instance, if I have a bunch of samples in here and I'm constantly going to this door and opening and closing, opening and closing, opening and closing, and opening and closing, I am exposing all of that material on the inside to that environment every single time that I open the door. So this is going to be a little bit better type of situation for long-term storage, or for storage of multiple samples at one time that can be taken out at one time, and not necessarily opening the door on a rotating basis like this. Over on the left-hand side, the smaller desiccators give you more control. So you know what goes inside of there is limited. You know that when those get opened and closed, only those limited number of things are going to be exposed. And sometimes there's only room for one sample and one sample only in those desiccators. And if that's the case, okay. And it might make more sense to use those types of desiccators for that purpose. But these are just two different types of desiccators that you'll see in a laboratory environment. Down here at the very bottom, you will often see that's where they will put the desiccant down here. And some people will just pour it and dump it into the bottom tray area, and other people will go through and pour it in a tray that you see here in the picture, and that will hold the desiccants. Again, that can be silica, or that can be something totally different. Finally, a picture of total suspended solids. Here are weighing dishes that they have placed the filter papers into, and you can see a variation of the suspended solids on those filter papers. Like visually, you know stuff is there because they were often turned brownish, beige, and then dark brown means, of course, probably very dirty, and then lighter beige just means a little less dirty than some of the other options. But visually, you can see that, and that is total suspended solids, and that is method 160.2. So just some visuals and some cues on what you're getting ready to see in the laboratory for this particular day. And again, we'll demonstrate how to process a sample both with a 161 and 162 combo, as well as a sample of just straight up 160.3. So that way you can see the difference a little bit better. All right, so good luck on the pre-lab assignment. Hopefully you'll be ready for the lab when you show up that day. And we'll have all the directions printed out for you. The data sheets are going to be printed out for you. And normally, ideally, we would do these in triplicate. So at least 3 portions of the water will get processed so we can take an average of the TSS and TDS. But for this particular lab experiment, we're only going to do 1 sample portion, and that is it. We're going to be doing 1 round of heating, and that is it. And then you will eventually put your data into a shared spreadsheet. So that way you've got multiple data points that you can go by. So that way we can do averages and standard deviations and confidence intervals a little bit later on down the road when everyone compiles and puts their data into the same spreadsheet for us. So with that said, good luck on the pre-lab assignment. I'll see you in the lab. We'll be ready to go, and I'll demonstrate how to do something for you. And then you'll just kind of mimic that after the fact. But folks, it's really just kind of like waiting around for an hour and getting it back in the desiccator. During that 1 hour of heat, that would be a great time to go work on some lecture stuff or some remaining lab stuff that you need to turn in. And 1 hour's time, your sample is going to be ready to be ding ding taken out of the oven, because guess what? Your cake is done.